All right, in this video, we are going over section 4.5, which is on derivatives and the shape of a graph. Okay, so a couple of the learning objectives that we're going to try to um, conquer here are 4.5.1. Explain how the sign of the first derivative affects the shape of a function's graph. Number 2, state the first derivative test for critical points. So we'll talk about what the first derivative test is. Number 3, use concavity and inflection points to explain how the sign of the second derivative affects the shape of a function's graph. Number 4, explain the concavity test for a function over an open interval. Number 5, explain the relationship between a function and its first and second derivatives. And then finally, to state the second derivative test for local extrema. Okay, so we'll briefly go over some of these. I don't expect to, maybe we won't cover all of it, but the there is a result, a corollary number three of the mean value theorem, which shows that if the derivative of a function is positive over an interval I, then the function is increasing over I. So, we've talked about this before, but essentially, if the slope of the tangent line is positive, then that means that the function is increasing. And we can see that uh, with multiple examples here. In each of these cases, from left to right, the function is increasing, and we can see that the slope of the tangent line is positive. So the derivative function is positive. And also, if the derivative has a negative value, then that implies that the function is decreasing. Okay, so we are going to use this information to help us locate local extreme values. Okay, so let's go ahead and take a look here. Uh, so one thing we said in section 4.3 was that if a continuous function has local extreme values, then it must occur at a critical point C. Okay. Uh, a function that has a local extremum at a critical point C, a function will have a local extreme value at C if and only if the derivative f prime switches sign as x increases through C. And so what this is talking about is, notice here we have a local max, a local maximum. Well, we can see that the derivative is positive before the local maximum, implying that the function is increasing, and the derivative is negative after the local maximum, uh, implying that the function is decreasing. So that's one thing to note. If we have another local max somewhere else, here the derivative is actually defined and it's equal to 0. But we can see that that behavior from before still holds. The derivative before the local max is positive and then becomes negative afterwards. And so even at a local minimum, the first derivative changes sign. The first derivative is negative before a local minimum. Oops, that's a really bad tangent line. And then the first derivative is positive after the local minimum. So, what does it say here? To test whether a function has a local extremum at a critical point C, we must determine the sign of f prime of x to the left and right of C. This result is known as the first derivative test. So we'll just briefly go over this. Um, as we mentioned in that picture, if the first derivative changes sign from positive when x is less than c to negative when x is greater than c, then f of c is a local maximum. So just to draw a local maximum, we can see that the derivative is positive. It changes sign to negative, and so the critical point in between must be a local maximum. Okay, if the sign changes from negative to positive, then f of c is a local minimum. And if f prime of c has the same sign before, if f prime has the same sign to the left of c and to the right of c, then f of c is neither a local max nor a local minimum. Okay, so let's go ahead and use this problem-solving strategy here um, to uh, uh, kind of demonstrate the first derivative test. Okay, and let's see here, which problem can we do? Um, let's take a look. Yeah, we'll just take a look at the one that's done there and just do it ourselves. So example 417 says use the first derivative test to find the location of all local extrema for f of x. And so f of x equals x cubed minus 3x squared minus 9x minus 1. So we can find the derivative. This is 3x squared minus 6x minus 9. We can factor out a 3. Since we want to find the critical points, we're going to set this equal to 0. And if we set this equal to 0, that requires us to factor this quadratic. So this is 3 times x minus 3 times x plus 1 equals 0. And so we can see that x minus 3 must be equal to 0, or x plus 1 is equal to 0. So x equals 3 or x equals negative 1 are the critical points. These are the locations where the derivative is equal to 0. So what we can do now is once we find the critical points of f, we divide the interval I into smaller intervals using the critical points as endpoints. And so what we're going to do, excuse me, is draw a number line. And we're going to split up the, real number line from negative infinity to positive infinity in this case, um, into, oh, wait, whoops. We have to put a negative here, so I'll write it in red. Negative 1. We're going to split up the real number line, and we're going to split it by using negative 1 and 3. And so now we have subintervals. The subintervals are from negative infinity to negative 1, uh, negative 1 to 3, and 3 to infinity. These are the subintervals that we're going to find the value, find the sign of f prime over. And so what we need to do is we need to use test points in each of these subintervals. And I'm going to choose fairly simple numbers. Negative 1, I will choose, let's choose, just for the sake here of choosing a random value, for this one here, I'm going to choose, um, actually, yeah, we'll stick to an easy number, 0. And then here, 4 would be a nice number. I'll choose 5 just to choose something different. Okay, so we want to know what kind of sign does the first derivative have in this interval from negative infinity to negative 1. And so we plug in negative 2 into the first derivative, and this is called the first derivative test. These are x values that we got for our critical points, and these are x values that we're testing, and f prime of x is what we're going to test. So let's do that. Let's do it in red here. F prime of x is written up here. We can use this version, or we can use the factored version, whichever one you like. So f prime of negative 2 is, starting with that factored version, 3 times negative 2 minus 3 times negative 2 plus 1. And this is going to be 3 times a negative 5 times a negative 1. That is a positive number. So positive 10, which is greater than 0. So that tells us the function is increasing. That f is increasing since the f prime is positive. Now let's go ahead and test at 0. F prime of 0 is going to be, here I'm going to plug into the original quadratic before we factored. You can plug into any equivalent form of the derivative. This is going to be negative 9. And the negative is the really important part there. So negative 9. This is less than 0. And so that tells us that over this interval here, the function is decreasing. And then finally, let's test 5. F prime of 5. This is going to be 3 times 5 squared minus 6 times 5 minus 9. So that is 75 minus 30. That's 45 minus 9, which is 36. Positive 36. This is greater than 0. And so the function is once again increasing. Okay, so then if a function is increasing and then decreasing and then starts increasing again, that tells us that we have a local maximum at x equals negative 1, and we have a local minimum at x equals 3. Okay. Okay, so that's exactly the information that's given here. And we can see we have a local maximum and a local minimum. Nice. Okay, now if we wanted to find the y values, we could plug in x equals 1 and x equals, oops, negative 1. I dropped the negative again. And x equals 3 into the original function. I don't think it asks us for that. Yeah, so we'll leave it at that. And you can see from the graph what they are. Okay, we'll continue. So now I do want to do a more complex problem. So here's example 4.18 is a good one because it's a little bit more complicated. So let's take a look at this one. So f of x is given here, and let's find the derivative. F prime of x is, we bring down the 1/3, so 5/3, x to the negative 2/3 minus 5/3 x to the 2/3. And so we need to do a little bit of algebra here. This is going to be 5 over 3x to the 2/3 minus 5x to the 2/3 over 3. And so we need to multiply that to get a common denominator. We should multiply by x to the 2/3 on the top and bottom. And so what we end up getting is 5 minus uh, 5x to the 4/3 over 3x to the 2/3. And so we are going to have multiple critical points, it looks like. The critical points are going to be where the derivative, and let's start with f prime of x is undefined. That is going to be where the denominator is equal to 0. So 3x to the 2/3 equals 0. You can see that you can just divide by 3 on both sides. And so x must be equal to 0. You can cube both sides and take the square root. X must be equal to 0. This is one critical value. Then, where is f prime of x equal to 0? Well, that would be exactly where the numerator is equal to 0. And so if we add the 5x to the 4/3 to the other side, and we divide by 5 on both sides, I'm going to write the x to the 4/3 first. And then here, yeah, let's show the work. I think we skipped it on the previous video. We can cube both sides, raised to the 3rd power. And so we get x to the 4th equals 1 cubed, which is 1. And then here, if we take the 4th root of both sides, then we need a plus or minus. So x equals plus or minus 1. Okay, so our critical points are positive, and negative 1, and 0. And so now we can make our line here for the first derivative test. Negative 1, 0, positive 1, x, f prime of x. Okay, so what are our test points? I'm going to pick, yeah, let's choose easy numbers. Negative 2, positive 2. We'll choose 1/2 and negative 1/2. Okay, so let's plug each of these into the first derivative. Uh, so let's see, our first derivative is, is this thing up here. So let's go ahead and plug in our numbers here. I'll do it in red. So let's start with 2. F prime of 2. This is equal to 5 minus 5 times 2 raised to the 4 over 3 over 3 times 2 raised to the 2 over 3. And we have calculators, but we could actually see here that if we factor out a 5 on top and we do 1 minus 2 to the 4th power is 16. So this is the 3rd root of 16. And the denominator is just 3 times the cube root of 4. We can see it looks like this is going to be a negative number because 1 minus the 3rd root of 16, we know that the 3rd root of 8 is 2, and so this is larger than that. So this is 1 minus a bigger number. So this should be negative. Let me punch it into the calculator to see exactly what it is. 5 minus 5. Okay, so I got approximately negative 1.595. Now, the main thing that matters is that it's negative. And so that tells us that the function is decreasing, that f is decreasing on this interval. And this function is actually, if you were to plug in a negative 2, this would, the result would be exactly the same because since we're raising to the fourth power, that negative is going to just be raised to the fourth power. An even number of negatives is also is going to be positive, and so we get the same result. And so we can say that on this interval over here, f is decreasing. So finally, we just have to do the 1/2. Uh, and the negative will also, those should uh, be the same. So let's go ahead and plug in uh, f prime of 1/2. Now, yeah, we have a calculator, so we can just plug in. The main question is we're asking is the numerator positive or negative? Um, and yeah, actually, one way we could do this without a calculator, I'm just kind of getting an idea here, just in case, we want to do this without a calculator. We can use the values, let's use 1/8, because 1/8 is a number we can take the cube root of. And so if we do 1/8, then this becomes 5 minus 5 times the cube root of 1/8 is 1/2. And so we get 5 minus 5/16 over 3/16. And we could see here that if we try to get a common denominator, multiplying by 16 on the top and bottom, then we get 75/16 over 3/16. And that looks to be 25. It's a positive number. So here we would say that this is where f is increasing. And in this segment here for negative 1/8 as our test point, f is increasing. Okay, so now we can conclude here, if f is decreasing and then increasing and then continues to increase and then finally decreases, then we are going to have a uh, minimum at -1, local minimum, local maximum at x equals 1. And then it looks like we have neither a local min or local max at x equals 0. Okay, so let's see. Uh, and do we have that? Yes. Yes, we do. Okay, so that's a very nice to see that our results match up exactly with this graph. Local minimum, local max. And then this is a critical point, but it ended up not being a local min or local max. All right, so let's see how long this video is. It is long enough. So, um, the first derivative test can be used. Now, I will just, yeah, let's say one more thing here about the second derivative test. Um, yeah, just very quickly here, we'll mention that the second derivative tells us about the concavity of a function. And so, uh, where is the result? Here, test for concavity. It says let f be a function that is twice differentiable over an interval I if f double prime of x is greater than 0, then f is concave up. Okay. And if the second derivative is less than 0, then f is concave down. Okay, so we could also use this to find local extrema. If it's concave up, like y equals x squared is, um, then that could imply that there's a local minimum somewhere. Or if it's concave down at a critical point, then that could imply that there is a local maximum. So concavity is also important to us. Um, and then, yeah, we also define an inflection point. This is where the concavity changes, where a function goes from being concave up to concave down. Okay, the point at which the concavity changes from positive to negative or negative to positive is called the inflection point. Okay, so let's go ahead and take a look at how we can use concavity to find local extrema. This is called the second derivative test. And basically it says if you find a critical point where the derivative is equal to 0, then if the second derivative is positive, meaning so there's a tangent line that is equal has a slope of 0. If you also see that the concavity is, so that the function is concave up, then there will be a local minimum at that critical value, critical point. And if the second derivative has a negative value, then there's a local maximum at that critical point. But there is one downside to this test. Well, if the second derivative is equal to 0, then the test is inconclusive. And in that case, let's see what it says here. Actually, note that for case number 3, when the second derivative is equal to 0, then f may have a local maximum, local minimum, or neither at C. For example, the functions f of x equals x cubed, x to the fourth, and x to the negative fourth all have critical points at x equals 0, and in each case, the second derivative is 0 at x equals 0. However, the function f of x equals x to the fourth has a local minimum, whereas negative x to the fourth has a local maximum, and x cubed does not have local extremum at x equals 0. So yeah, in those cases, what you want to do is you can look at the first derivative test and see what that tells you. Okay, so let's do our last example here, and we'll do one that's not that complicated just to finish out here. Ah, yes, perfect. This example that they give us, um, let's go ahead and do that one. So it says, use the second derivative to find the location of all local extrema for this function here. Okay, so there's our function, f of x. Let's find the derivative so that we can find the critical values. So that the derivative is 5x to the fourth minus 15x squared. We can we're going to factor this, so we can factor it out of 5x squared to get x squared minus 3, x squared minus 3. Yep. Set that equal to 0 to find the critical points. And so the critical points are at x equals 0, or when x squared minus 3 equals 0. So if we add the 3 to the other side and take the square root, x is equal to plus or minus the square root of 3, or x equals 0. These are the critical values. I'll put them on a number line here uh, just to show where they are here roughly. 0 and uh, positive root 3. And so we know that the first derivative is equal to 0 at each of these points. What we want to know, though, is what is the second derivative at each of these points? So let's find the second derivative. F double prime of x is equal to 20x to the third minus 30x. This factors to, let's see here, 10x times 2x squared minus, what is that, minus 3? Uh, okay, that seems okay. And so, let's see, use the second derivative to find the location of all extrema. Uh, okay, so, okay, so we find the second derivative, and really all we need to do, actually, I'm doing too much here, I'm factoring it, but all we need to do is really just plug in our critical values. So let's go ahead and do that here. Um, and let's make sure we found them. Yes, we found them correctly. There they are. Now let's just plug them in. So f prime, f double prime of the square root of 3. I'm going to use this factored form since there's a square in it. This is going to be equal to 10 times the square root of 3 times 2 times the square root of 3 squared minus 3. This is 10 square root 3 times the square and the square root will cancel. So we get 6 minus 3. That's positive 3. This is going to be a positive number. I don't really care what the number is. Let's just say positive 30 root 3, whatever that is. This is greater than 0. And so that tells us that the function is concave up, since this is the second derivative. And so if you have the function being concave up at this critical value, that tells you that there's going to be a local minimum there. F double prime of negative root 3. Let's just do that one. That's going to be 10 times negative square root 3. 2 times negative root 3 squared minus 3. And so we can see here that this is just going to be negative 30 root 3. The square and the square root will cancel, but when you square a negative, that will also go away. And so we end up getting just a negative number. So here, we know that the function is concave down at this critical point. So there must be a local max there. And then finally, the last one, f double prime of 0. F double prime of 0 is just going to be 10 times 0 times 2 times 0 squared minus 3. That's 0. And so at this point here, we can't tell if there is a local minimum or local max. The second derivative test is inconclusive. So if we really wanted to know if there was a local maximum or local minimum, we could use the first derivative test and test to the left and to the right of 0 to see if the first derivative changes sign and if there's a local max or min. Okay, so let's go ahead and see. Yeah, the second derivative is inconclusive at 0. And it does say To determine whether f has a local extrema at x equals 0, we apply the first derivative test. And so they do that there. Um, we conclude that f is decreasing on both intervals, to the left and to the right of 0, it looks like. So f does not have a local extrema at x equals 0, as shown in the following graph. Okay, so the second derivative test tells you about concavity. That can be used to determine where there's a local max or local min, or where, well, if the test is inclusive, you can take a look at the first derivative test. In this case, the first derivative was negative, and then after this critical point, it was also negative, and so that implies that there is neither a local max or local min there. All right, so let's take a look at this last paragraph. It says, we have now developed the tools we need to determine where a function is increasing and decreasing, as well as acquired an understanding of the basic shape of the graph. In the next section, we discuss what happens to a function as x goes to positive or negative infinity. At that point, we have enough tools to provide accurate graphs of a large variety of functions. All right, very good. Hopefully you enjoyed that video. If so, leave a like on the video or leave a comment, and I will try to continue producing these videos.